we're going to look at some more examples of modeling with our trigonometric functions. So here we have this graph which shows the data from the Mauna Loa Observatory. I probably said that wrong, I'm sorry. And this is the carbon dioxide that's in the atmosphere. So as you can see, it's going up, which also is contributing to our global climate change and increasing our global temperatures. Okay? So in addition to increasing this, we have throughout the seasons that there's a sinusoidal variation. So as you notice, you've got these little curves in between here that follow that sinusoidal. So as we're going up and down in the season, it's slowly starting to rise over the years. Okay? So right here in this table, we have a section between 2006 and 2008 from this information. So we're going to write a trigonometric model based on, it says sine. We're going to do cosine function. That approximates the carbon dioxide change in parts per million with a function c of t, where t is the year. Okay? So I first need to use this table to find our maximum and minimum values. So I've already highlighted our max and mins. I'm looking at the max and mins of the y values. So this is the highest that our y values go, and this is the lowest that our y values go. So in 2007.3, we're up at 383.9. And then in 2007.8, we're at 376.3. Right, so our equation's going something like this. Okay. Now, because we're going by hand, we don't take into consideration all the rest of these. There is a way that your calculator can take into consideration all of these different points and come up with a more precise graph that models all of the points rather than just 2 of the points. When you model by hand, we can only take into consideration the 2 points. Okay? So our max and our min to get us there. So that means that our amplitude can be max minus min cut in half. So 383.9 minus 376.3 cut in half. So if we do that, that gives me 3.8. And then the midline is going to be the minimum, which in this case is the 376.3 plus the amplitude of 3.8. So if we do the 3.8 plus the 376.3, that gives us 380.1. So that's our D value. This is our A value. Okay. To find the period change, remember the period we can find by doing 2 times subtract your x's. So if we do double subtract the x min, the x from the minimum and the x from the maximum, we're going to do 2,000, 2 times 2007.8 minus 2007.3. Whoops, that's a bar. So then that gives us 2 times, that just gives us 0.5, which if we do double 0.5, that just gives us 1. Okay. Which should make sense if you're thinking in terms of our weather, right? Our weather varies on a yearly basis. So this is telling us that it's a year, which should make sense to us. Okay. So the period is a year, but then we need to find the b value. Well, the b value we can find by doing 2 pi divided by the period. Well, in this case, that's 2 pi divided by 1, which is 2 pi. So now we have A, B, D. Our C is the horizontal shift. So that we're talking about how far over we started. So on this, we started over by this amount. So we shifted right by 2007.3. Okay. So that means we can now write our equation. I need to decide if this is sine or cosine and if it's positive or negative. Well, this is a smiley face, so smiley face means that it's going to be a positive cosine. So now I can write my equation, y equals, or actually, see here how it tells us to write it as c of t. So our carbon concentration in parts per million. Notice that's what the Y value is of the carbon dioxide. In relation to our time is the amplitude, which is 3.8. It's a positive cosine. The B value is 2 pi. And then it's x minus, we shifted right by 2007.3, so we have a minus 2007.3. No, 2007.3, sorry. And then plus our midline, which is our D value, which is 380.1. Okay. So this is our equation that we can come up with for our trigonometric model. So now we can look at some more examples. So this one we have a story problem. So naturalists have found that animal populations such as the Arctic lynx, some species of fox, and certain rabbit breeds tend to fluctuate sinusoidally, meaning that it's going up and down, over 10-year periods. Suppose that an extended study of a lynx population began in 1990, and in the third year of the study, the population had fallen to a minimum of 2,500. In the eighth year, the population hit a maximum of 9,500. Okay? So we need to pull out information from this. The information that we've been utilizing to get our amplitude and midline is minimum and maximums. So this part right here that it's telling us the minimum of 2,500 and the maximum of 9,500 is important. So there I can use that to find my amplitude. So the amplitude is just going to be 9,500 minus 2,500. That looks like a 4. 9,500 minus 2,500. Cut in half. Okay. So that gives us 3,500. Okay. So now that we have that information, that means that we can find our midline. So our midline is going to be the max minus the amplitude or the min plus the amplitude. So I think I did min plus amp, so we'll do 9,500 minus 3,500. So if we do 9,500 minus 3,500, that leaves us with 6,000. So our D value is 6,000, and our A value is the 3,500. Okay. Well, now we need to figure out something to do with the period. So I'm going to go back and look. So we began our study in 1990. And in the third year of the study, the population had fallen to a minimum. So at year 3 is when we were at the 2,500, year 3 of the study, which correlates to 1993. And then in the 8th year of the study, we had hit a maximum of 9,500. Okay. So we're going from the third year to the 8th year. So between the third and the 8th year is a total of 5. So the period is going to be 2 times the 8 minus the 3, which gives us 2 times the absolute value of 5, which gives us 10. Now, this piece of information here is also told to us in the problem right here, that it fluctuates sinusoidally over 10-year periods. Remember, period is another name for cycle, or the wavelength. So the period is 10. So we could have found it using our x values or using the information that was given to us. But we still need the b value. The b value we find by doing 2 pi divided by the period. So in this case, since the period is 10, we're going to do 2 pi tenths, which then simplifies to pi fifths. Okay. Now I'm going to draw a quick representation. So 3 and 8. At 3, we're at 2,500, and at 8, we're at 9,500. So my picture kind of looks like this, which means it's a negative cosine graph. It also means that I've got this horizontal shift that it's gone right by 3. So now I can write my equation. So we have y equals a, which is the amplitude, which was 3,500, times by, it's a negative cosine because it was a frowny face. The b value is pi fifths. I have to say, hey, we shifted over by 3. Remember, from the graph to the equation, it changes sign, so x minus 3. And then plus the midline, which we found to be 6,000. Okay. So then it says use the model to predict the lynx population in the year 1996, which obviously it's not predicting now because it's past 1996, but when this information was from 1996 hadn't happened yet. So now this is where we need to go back and look. The population study began in 1990. So 1996 is 6 years after that. So that means that 1996 is the same thing as x equals 6. So that means that if I plug 6 into this equation, that will predict the amount of lynx in the year 1996. So we have y equals negative 3,500 cosine of pi fifths times 6 minus 3 plus 6,000. Okay. And I'm just going to put this into my calculator so it looks like this entire thing. Now, we are in radians because we're using pi's. So you need to make sure your calculator is switched to radian. So you can do negative 3,500 cosine of pi fifths. Then you need to have another set of parentheses times by 6 minus 3, which you could simplify to be 3, and then plus 6,000. Okay. So when you plug that into your calculator, you should get 7081.559. Okay. So really, since we're talking about a population of animals, right, there's not portions of animals that we're referring to. So we're going to estimate that the population of lynx in 1996 is 7,082. Right? So these things can help us predict certain things. They use information to predict how many children, like the birth rates. They predict how many children are going to be in schools and fund the schools based on those predictions or the birth rates that we have so that you can tell what's going on. They use it nearby at Intermountain Healthcare. During the winter, our cases of respiratory disease that I can't remember the name of right now goes up. So they predict how much medicine they're going to be needing to treat that disease based on the data. So they're using data to predict information to help prepare for certain events or things that they need. Okay. If we look at this next one, this one is a Ferris wheel, which we've dealt a lot with. So if you're given information, if there's any way that you can draw it, like a Ferris wheel, then you should. So a Ferris wheel is 250 feet in diameter. So that means that this is 250 feet. We've got something that holds it. And revolves around 40 seconds, every 40 seconds when it's in motion. Okay? So 40 seconds. Your step up to the seat on the wheel at the loading spot is 2 feet above the ground. So right here, when I'm loading onto the Ferris wheel, this is 2 feet off the ground. Okay. Oh, I didn't read that right. So the loading spot is 2 feet above the ground, and you're sitting 4 feet above the ground to start. So this is 4. So let's fix that, sorry. 4 feet. Okay. So we want to figure out the formula to figure out the height of your seat at any given time t. Okay? So that means that our minimum height is the 4 feet off the ground when I'm sitting in my seat at the loading dock at the lowest point. Okay? The highest is going to be that 4 feet plus the 250. So my max height is 254. Well, now that we've found the minimum and the maximum, I can find both the amplitude and the midline. So the amplitude is going to be 254 minus 4 cut in half, which is 250 cut in half, which is 125. The midline is going to be the minimum plus the amplitude, so 4 plus 125, or the max minus the amplitude. So either way, you're going to get to 129. Okay. So this is our D value. Oops, 129. This is our A value. So we have 2 of our things so far. Okay. So it takes 40 seconds to go around. Now, if you're thinking about your Ferris wheel, if you're starting at the bottom of the Ferris wheel, then you're going to go up to the top, and then you're going to come back down. So I have made this shape, which is a negative cosine graph. Okay. So then I also need to know the period. Okay. The period, it takes 40 seconds to go around. The go around is this shape, which is a wavelength or a period. So that means that the period is 40 seconds. Okay? Again, if you think per 1 unit of time is a frequency, this is not per 1 unit of time. This is 40 seconds. So this is not a frequency, which means it's a period. Okay? So the period is 40 seconds, which means I can find the b value. So b is 2 pi divided by 40, which gives us pi 20ths. Okay? Now, there's nothing to say that I start the timer and then I wait a few seconds and I start the Ferris wheel. So that means that our c is at 0, right? We're starting our time and the Ferris wheel at the same time. Okay? So I don't have any horizontal shifting. So my axis will look something like that. Okay? So that means that I can now put all this information together to get my equation. So we're going to do our height. So notice it gives us the variable of h. So the height at any time, so it's really h of t, is going to be the amplitude, which is the 125. It's a negative cosine of b, which is pi 20ths, and then x minus 0 because we're not shifting left or right at all, and then plus our midline, which is 129. Okay. So notice I created the picture to figure out where my max and min were. Once you have your max and min of your heights or your y values, you can find both your amplitude and your midline, and you have half the numbers that you need. Then you need to figure out either from the situation or from x values what the period is. Then you can find your b value. You can create a sketch of the scenario that's happening to figure out, is it going to be sine or cosine? Most of our modeling that we're going to do is going to be from minimum and maximum points. So most of the modeling ones that we're going to do are going to be coming from a cosine perspective. Doesn't mean you couldn't find a sine. It just means that it's more tedious. Okay? So I could simplify this equation to h of t equals negative 125 cosine of pi halves x plus 129. Okay? And then this would be my equation. So if I wanted to know how far I am at 20 seconds, right? At 20 seconds, if we were to plug that in, since that's half of 40, we should get our maximum height of the 254. So if we plug 254 in there and then plug that into our calculator, we should get the... or not 254 that we plug in. If we plug the 20 in, then we should get the 254 as our answer. Okay? So that's how you set up and create your equations from information that you're given.